Hi there, Professor Barber here. This lesson is titled Transformations of Functions. In this lesson, we learn how the transformations of shifting, reflecting, and stretching and shrinking affect the location, orientation, and shape of the graph. Upon successful completion of this lesson, you will 1. Be able to perform rigid transformations of functions. 2. Be able to perform non-rigid transformations of functions. And 3. Be able to determine whether a function is odd, even, or neither. Roman numeral 1. Rigid transformations. Rigid transformations are vertical and horizontal shifts and reflections. The shape of the graph is not affected during a rigid transformation, only its location. So let's look at vertical and horizontal shifts. Let's suppose c is greater than 0. To graph y equals f of x plus c, we shift the graph upwards c units. To graph y equals f of x minus c, we shift the graph downwards c units. Notice that when we add or subtract to the function, these are vertical shifts. To graph y equals f of the quantity x minus c, we shift the graph to the right c units, and to graph y equals f of the quantity x plus c, we shift the graph to the left c units. Note that horizontal shifts are made when we add or subtract to the argument. Use the graph of f of x equals the square root of x to sketch each transformation. Let's begin this exercise by first getting the base graph, which is f of x equals the square root of x. Under an even root, your acceptable values have to be non-negative, so when I select my x choices to compute the corresponding y's, I'll start with 0, 1, and remember this is a square root function, so I'm going to pick 4 and 9. The square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, and the square root of 9 is 3. Let's plot these 4 points, 0, 0, 1, 1, 4, 2, and 9, 3. And connect, and what we have is the graph of the square root function. Part A, y equals f of x plus 2. The plus 2 is on the outside, that's in addition to the function, so we take each function value and shift it up 2 units. I'll start with the origin and go up 1, 2. The next ordered pair, I'll go up 1, 2. The next one I plotted, I'll go up 1, 2. And the last point I plotted, I'll go up 1, 2 and connect. And now that is my square root function shifted up 2 units. Part B, y equals f of the quantity x minus 2. When the change happens to the argument's the stuff inside the parentheses, then your shift is horizontal. The minus 2 means you go to the right 2 units, so we'll start with a base function, and each point I plotted, I'll move it to the right 1, 2 units, 1, 2 units, 1, 2 units, and 1, 2 units. Knowing the basic shape of the graph, I'll connect it, and there is my graph that's shifted to the right 2 units. Let's do part C, y equals f of x, and that entire function minus 4. That tells us we have yet another vertical shift, but now it is down 4 units. So each point that we have, that we plotted, let's just go down 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And 1, 2, 3, 4. Connect the points. Ha! And we have the square root function shifted down 4 units. And part D, y equals f of the quantity x plus 3 and then minus 1. This tells us we have 2 shifts, a horizontal and a vertical. The x plus 3 tells us that we actually shift left 3 units, and the minus 1 tells us that we go down 1. So let's take each point and go back 3, down 1, back 3, down 1, back 3, down 1, and back 3, down 1. Connect those points, and now we have the graph of f of the quantity x plus 3 minus. Reflecting graphs about the coordinate axis. To graph y equals negative f of x, reflect the graph of y equals f of x about the x-axis. This is a top to bottom or bottom to top shift. To graph y equals f of negative x, reflect the graph of y equals f of x about the y-axis. This is a side-to-side shift. Use the graph of f of x equals the square root of x to sketch each transformation. The graph of f of x equals the square root of x is already sketched. The points I used were 0, 0, 1, 1, 4, 2, and 9, 3. Notice this is just 1/2 of a parabola sideways. Let's go to A. Y equals negative f of x. That transformation, the negative is affecting the function. That means we transform from either top to bottom or bottom to top, and we do this about the x-axis. So let's take each point and reflect it about the x-axis. The 0, 0 stays the same. The 1, 1 becomes 1, negative 1. The 4, 2 becomes 4, negative 2, and 9, 3 becomes 9, negative 3. Let's connect the points. And now we have the graph of y equals the square root of x reflected about the x-axis. B is y equals f of negative x. Notice that the negative is in the parentheses, which means it's affecting the argument. And when it is affecting the argument, we reflect it about the y-axis. Y-axis means side to side, so let's take each point. The origin stays the same. 1, 1 becomes negative 1, positive 1. 4, 2 becomes negative 4, positive 2. And I'm out of graph paper here, so I'll just connect the points. And we get it. The graph is just flipped about the y-axis. And now we're ready to do C. Y equals the negative of f of negative x. That's a transformation top to bottom and side to side. So if we take the original point, the 0, 0 stays the same. The positive 1 becomes negative 1, negative 1. 4, 2 becomes negative 4, 2. We connect the points. And that graph is reflected about the x-axis and the y-axis. Roman numeral 2, non-rigid transformations. Non-rigid transformations affect the shape of the graph, not their location. The graph actually retains its identifying shape. These transformations stretch or compress that shape. So, let's assume A is greater than 1 and 0 is less than B is less than 1. A vertical stretch by a factor of A, that's a number greater than 1, is indicated by y equals A times f of x, and a vertical shrink by a factor of B. B is a number between 0 and 1, is indicated by y equals B times f of x. In trig, a vertical stretch or compression affects what is more commonly called the amplitude. Continuing with the assumption that A is greater than 1 and B is between 0 and 1, A horizontal stretch by a factor of a is denoted by y equals f of, and in the argument a times x, and a horizontal shrink by a factor of b is denoted by y equals f of, and in the parentheses b times x. In trig, this graphical transformation affects what is called the period. Use the graph of f of x to sketch each transformation. The graph we're transforming consists of 4 connected line segments. The first segment increases from -5, -4, in quad 3 to -2, +1. In quad 2, decreases from -2, 1 in quad 2 to 1, -2 in quad 4, and increases from 1, -2 in quad 4 to 3, 3 in quad 1, and decreases from that point to 4, 1, also in quad 1. Let's look at y equals f of 1/2 of x. The horizontal effect works somewhat counterintuitively. If the number multiplied to x is greater than 1, the horizontal gets compressed, and when the factor is between 0 and 1, as with this example, the horizontal gets stretched. To reduce the possibility of confusion, just remember that with the x, we divide. So, let's do it again. Y equals f and the quantity 1/2 x. The 1/2 is divided to the argument or the x value of the function. This means the period or the width of the graph of the function is affected. To get the graph of the transformation, the y value remains exactly the same, and the x value is, I'll repeat, divided by a factor of 1/2. So, the ordered pair -5, -4 becomes -10, -4. Remember, -5 divided by 1/2 is actually multiplying by 2. So, -2, 1 becomes -4, 1. Again, if you divide by 1/2, you're multiplying by 2. The ordered pair 1, -2 becomes 2, -2. The ordered pair 3, 3 becomes the ordered pair 6, 3. The ordered pair 4, 1 becomes the ordered pair 8, 1. We'll mark these transformed ordered pairs on the grid. So let's start with -10, -4, -4, +1, 2, -2, 6, then up 3 spaces, then 8, up 1. Let's connect. That's supposed to be a straight line. Observe that the entirety of the original graph now requires double the horizontal width. Part B, y equals 1/2 of f of x. The 1/2 is multiplied to the y value of the function. This means the amplitude or height of the graph of the function is affected. To get the graph of the transformation, the x value remains unaffected and the y value is multiplied by a factor of 1/2. So, the ordered pair -5, -4 transforms to -5, -2. Remember, we are multiplying by 1/2. The ordered pair -2, 1 becomes -2, 1/2. The ordered pair 1, -2 transforms to the ordered pair 1, -2 multiplied by 1/2 is -1. The ordered pair 3, 3 becomes 3, 3/2. And finally, the ordered pair 4, 1 becomes 4, 1/2. Let's mark these transformed points on the grid. So we'll have -5, negative 2, negative 2, 1/2, 1, negative 1, 3. 3 halves is actually 1.5, and 4 halves. Now we'll connect the points. We observe that the entirety of the original graph now fits vertically in 1/2 of the original height. Y equals 2 times f of x. The 2 is multiplied to the y value of the function. This means the amplitude or the height of the graph of the function is affected. To get the graph of the transformation, we are going to transform the ordered pairs. The x values remain unaffected, and the y value is now multiplied by a factor of 2. So, the negative 5, negative 4 becomes negative 5, comma, negative 8. Remember, the negative 4 is now multiplied by 2. The ordered pair, negative 2, comma, 1, becomes, the negative 2 remains the same, and 1 times 2 is 2. The ordered pair, 1, comma, negative 2, becomes, the 1 remains the same, negative 2 times 2 is negative 4. The ordered pair 3, comma, 3 becomes 3, comma, 6, because 3 times 2 is 6. And finally, 4, comma, 1 becomes the ordered pair 4, comma, 2. Let's mark these transformed ordered pairs on the grid. So I'll mark negative 5, comma, negative 8, negative 2, comma, 2, 1, comma, negative 4, 3, comma, 6, and let me locate 4, comma, 2, here it is, and let's connect these points. Let's observe that the transformed graph is now twice the height of the original graph and still the same width. D. Y equals f of the expression 2x. Now remember, this is horizontal. It is in the argument. The 2 is divided to the argument, the x value of the function. This means the period or the width of the graph of the function is affected. To get the graph of the transformation, the y value remains the same, and the x value is divided by a factor of 2. So, the ordered pair negative 5, comma, negative 4 transforms to negative 5 halves, comma, negative 4. The negative 2, comma, 1 transforms to negative 1, comma, 2. 1, comma, negative 2 transforms to 1/2, comma, negative 2. 3, comma, 3 transforms to 3 halves, comma, 3. And 4, comma, 1 transforms to 2, comma, 1. Let's mark these points on the grid. So we'll go to negative 5 halves, which is 2.5, right? So we'll go negative 2.5 down, negative 4. Negative 1, up 1, 1/2, down 2. 3 halves is 1.5, so we'll go 1.5 over, and then up 3, and finally we go to 2, 1. Now we can connect these points. And what we see is that the horizontal width has been scrunched or compressed to half the original width. Order of transformations. The order in which the shifts, stretches, and reflections are performed must follow the same rules as in algebraic simplifications. Recall PEMDAS, parenthesis first, then exponents, then multiplication or division, reading from the left to the right, whichever appears first, then addition and subtraction, again reading from the left to the right, whichever occurs first. Thus, we transform the graph of a function in the following order. 1. We do all reflections, that's multiplication, first, then 2, all stretching and shrinking are performed. That's also multiplication. And then finally 3, the shifting that has to do with addition or subtraction is performed next. Find the ordered pair that would correspond to 2, -3 when the following transformations are performed. Part A. Y equals f of x minus 1 plus 5. Well, let's see, these are all addition or subtraction, so the order doesn't matter. The minus 1 means that we shift to the right 1, and plus 5 means we shift up 5. So if we're looking at the ordered pair that starts with 2, 2 is the horizontal motion, so we're going to shift to the right, that's add 1, and then -3, we shift up 5, so we'll add 5 to the y value, so that transformed ordered pair is 3, because that's 2 plus 1, the -3 plus 5 is 2, so 3, 2. Let's do the same thing for B. Y equals negative f of x minus 4. Now this one actually has a multiplication, and the minus in front of the f of x means that we reflect the y value over the x-axis. Okay? If you think about that for a moment, that means you're going to switch the sign of the y value. So doing the first step, the 2, -3 becomes, flipping it over the y-axis, the -3 becomes the positive. Now, next step, so step 1 was the reflection, step 2 is the addition or subtraction, and the -4 means now you shift down 4. The up and down mean that you affect the y, so the 2, 3 then becomes 2, 3 minus 4 would be -1. The order of operations is very important. Remember, order of operations matters in transformations just as it does in arithmetic. Roman numeral 3, even and odd functions. Let f be a function. F is even if f of -x equals f of x for all x in the domain of f. The graph of an even function is symmetric with respect to the y-axis. What that means is for a given image of a graph, let's say it's increasing from the third quadrant through the second and it touches the y-axis. If the function is even, then the image of that graph is reflected, just like looking in the mirror, on the other side of the y-axis. Now, let f be a function. We say f is odd, not peculiar, but odd, if f of minus x equals f of x for all x in the domain of f. What this means is that a graph is, well, let's say the graph of an odd function is symmetric with respect to the origin, and this is a difficult thing to visualize. If you're looking at ordered pairs, what you do is change the signs, SIGNs, of both the x and the y-axis. A typical and easy example of an odd function is the cubic function, and that is both symmetric with respect to the origin and an odd function. Determine whether the following functions are even, odd, or neither. A. F of x equals x to the 5th plus x. The definition of odd or even says if it's even, f of minus x equals f of x. If it's odd, f of minus x equals minus f of x. So let's compute f of minus x. That is, let's compute f of negative x. So we're going to substitute in negative x. Every place there is an x. So we've got negative x to the 5th plus, and in parentheses, negative x. Let's do some algebraic simplification. Negative x to the fifth means negative x times negative x times negative x times negative x. Yes, 5 times negative x. So this can also just as well be written as the negative of x to the fifth. And for the plus negative x, write it as negative x. Let's factor out a negative from each of those terms. Then we get negative of x to the fifth plus x. And lo and behold, that's the original function. We've got negative f of x. So we have shown that f of minus x equals minus f of x. And when you do that, we have demonstrated that this function is odd. Let's do a similar thing for part B. G of x equals 1 minus x to the fourth. We're going to compute g of minus x. So every place there's an x, replace it with negative x. 1 minus negative x to the fourth. That's equal to 1 minus a negative raised to an even power is even, so that's x to the fourth. So 1 minus x to the fourth is actually the original function g of x. We have demonstrated that g of minus x equals g of x. And so by the definition, that's an even function. Part C. H of t equals 2t minus t squared. Let's compute h of minus t. Every place there's a t, we'll replace it with a negative t. So you have 2 times negative t minus negative t quantity squared. The first term, the product of 2 and negative t, becomes negative 2t. And on the second, the minus stays put, but a negative raised to an even number is t squared. So negative 2t minus t squared, and that does not look like 2t minus t squared. So what this has shown is that h of minus t does not equal minus h of t, and h of minus t does not equal h of t. These 3 dots looks like the corners of an equilateral triangle is read. Therefore, we say that h of t is neither odd or even.